Calculating sums from a given $th term expression. Hello everyone, welcome to today's session. To start off, let's take a look at our topic, calculating sums from a given nth term expression. Now, if you look at the first point here, you'll remember that in our previous lessons, we focused on finding the sum of an arithmetic progression, or AP, in a very straightforward way. Back then, we were always given the first term, which we call a, and the common difference, which we call d, explicitly. It was quite simple because all the pieces of the puzzle were already laid out for you. However, as we move into more advanced mathematical problems and real-world applications, things get a little more interesting. You won't always be handed a neat list of numbers. Instead, you'll often encounter an AP that is presented as a functional expression for the nth term, which we denote as a sub n. This is essentially a formula where the value of the term depends on its position in the sequence. So, the goal of this tutorial is to bridge that gap. I am going to show you exactly how to transition from working with that general expression for the nth term to calculating the total sum of the entire series. By the end of this lesson, you'll be able to take a formula and turn it into a total sum with confidence. Understanding the concept. Think of a functional expression for the nth term as a mathematical rule or a recipe. It's a formula that tells you exactly what value any term in your sequence will have, provided you know its position, which we call n. To make this concrete, let's look at the example on the slide. an equals 3 plus 2, and this formula is incredibly powerful because it allows you to jump to any position in the sequence without having to write out all the numbers in between. If you want the first term, you just plug in 1 for n. If you need the 10th term, or even the 100th term, you simply substitute that specific value for n into the formula. However, there is a crucial distinction you must keep in mind as we move forward. If your goal is to find the total sum, which we denote as Sn, you cannot simply plug n into this n expression and expect a total. The expression n only gives you the value of a single, specific term. To find the sum, we need to perform a bit of extraction first. We need to take this rule and pull out the two fundamental building blocks of an arithmetic progression. The first term, which we call a, and the common difference, which we call d in the next slide. I will show you the exact step-by-step procedure to do just that. Now that we've established that we are moving from a simple list of numbers to a more general functional expression, let's really dive into what this concept means. Step-by-step procedure. Now that we understand that an nth term expression is essentially a rule for finding any term in a sequence, let's look at the actual strategy you'll use to solve these problems. To calculate the sum of a series when you are given an nth term expression, you don't need to guess. You simply follow these 3 manageable steps. Step 1. Generate the first few terms. Since we can't use the formula for the nth term directly to find a sum, we need to turn that expression into actual numbers. You do this by substituting n equals 1, then n equals 2, and then n equals 3 into your given expression. By finding the first, second, and third terms, which we call a 1, a 2, and a 3, you achieve 2 things. First, you confirm that the sequence is indeed an arithmetic progression because you'll see a consistent pattern. And second, you get the specific numerical values we need for our final calculation. Step 2. Identify a and d. Once you have those numerical terms in front of you, your job becomes much easier. The first term, which we represent with the letter a, is simply the value you found for a 1. Next, we need the common difference, represented by the letter d. To find this, just subtract the first term from the second term, which is a 2 minus a 1. Step 3. Apply the sum formula. Now you have all the ingredients required for the final step. You have your a, your d, and the number of terms, n, which is usually given in the problem. All that's left is to substitute these values into the general sum formula. That formula is S sub n equals 1/2 of n multiplied by the quantity, 2a plus the quantity, n minus 1 times d. In the next slide, I'm going to walk you through a concrete mathematical example so you can see this exact 3-step process in action. Worked example 1, mathematical application. Here is the problem. We are given the nth term of an arithmetic progression, which we denote as a sub n, equal to 3 plus 2, and our goal is to find the sum of the first 10 terms. To solve this, we will follow the exact steps we just discussed. First, let's perform step 1, which is to calculate the first few terms to see the sequence in action. We do this by substituting the position number, n, into our formula. For the first term, where n equals 1, we have 3 plus 2 times 1, which simplifies to 3 plus 2, giving us 5. Next, for the second term, where n equals 2, we get 3 plus 2 times 2, which is 3 plus 4, resulting in 7. And for the third term, where n equals 3, we have 3 plus 2 times 3, which is 3 plus 6, giving us 9. So looking at our results, our sequence is 5, 7, 9, and so on. Now let's move to step 2, where we identify our key parameters, a and d from our calculations. The first term, a, is simply the value of our first term, which is 5. To find the common difference, d, we subtract the first term from the second term. That is 7 minus 5, which leaves us with a common difference of 2. Finally, we reach step 3, where we apply the sum formula. In this specific problem, we are looking for the sum of 10 terms, so n equals 10. We already know that a equals 5 and d equals 2. Let's plug these into the formula for s sub n, which is n divided by 2, multiplied by the quantity of 2a plus the quantity of n minus 1, times d. Substituting our values, we get 10 divided by 2, multiplied by the quantity of 2 times 5, plus the quantity of 10 minus 1, times 2. Simplifying inside the brackets, 10 divided by 2 becomes 5. Inside the brackets, 2 times 5 is 10, and 10 minus 1 is 9. So the expression becomes 5, multiplied by the quantity of 10 plus 9 times 2. Continuing the simplification, 9 times 2 is 18, so we have 5 multiplied by the quantity of 10 plus 18. Adding the terms inside the brackets gives us 5 multiplied by 28. When we multiply 5 by 28, we arrive at our final result of 140. Therefore, the final answer is that the sum of the first 10 terms is 140. Now that we have gone through the theory and the 3-step procedure, let's put it all into practice with our first worked example. To solve this, we will follow the exact steps we just discussed. In the next slide, we will see how this same logic can be applied to a real-world scenario involving solar panel installation. Worked example 2, real-world application. Imagine a technician is working on a large roof installing solar panels. Because of the specific layout of the roof, the work becomes slightly more predictable as they go, meaning the number of panels installed each hour increases linearly. We are given a formula for the number of panels installed in the nth hour, which is a sub n equals 10 plus 5, and our goal is to find the total number of panels installed after 8 hours. To solve this, we will follow the exact same 3-step procedure we just practiced. First, let's generate the first few terms to see the sequence in action. For the first hour, where n equals 1, we substitute that into our formula, 10 plus 5 times 1, which gives us 15 panels. In the second hour, where n equals 2, we get 10 plus 5 times 2, which is 20 panels. And for the third hour, where n equals 3, we have 10 plus 5 times 3, resulting in 25 panels. So our sequence of panels per hour is 15, 20, 25, and so on. Step 2 is to identify our AP parameters. From our calculations in step 1, we can clearly see that our first term, is 15. To find the common difference, d, we subtract the first term from the second, 20 minus 15, which gives us a common difference of 5. Finally, step 3, we apply the sum formula. We are looking for the sum of the first 8 hours, so our n is 8. We have r as 15 and our d as 5. Let's plug these into the formula. S sub n equals n divided by 2 multiplied by the quantity, 2a plus n minus 1 times d. Substituting our values, we get 8 divided by 2 multiplied by the quantity, 2 times 15 plus 8 minus 1 times 5. Let's simplify this step by step. 8 divided by 2 gives us 4. Inside the brackets, 2 times 15 is 30 and 8 minus 1 is 7. So we have 4 multiplied by the quantity, 30 plus 7 times 5. Continuing the simplification, 7 times 5 is 35. Now we have 4 multiplied by the quantity, 30 plus 35. That leaves us with 4 times 65. When we multiply 4 by 65, we get a final result of 260. Therefore, the final answer is that the technician installed a total of 260 solar panels over the course of 8 hours. Now that we have mastered the pure mathematical application in our first example, let's see how this concept applies to a real-world situation. This will help you see why being able to transition from an nth term expression to a total sum is such a valuable skill. Before we move on to some important tips on avoiding common mistakes, notice how the formula allowed us to jump straight from a rate of change to a total accumulation. Common mistakes to avoid. First, a very common mistake is confusing the nth term, which we call a sub n, with the sum of the terms, which we call s sub n. It is easy to see a value and think it's the total, but remember the distinction. A sub n represents the value of just one single position in the sequence, whereas s sub n represents the accumulation, or the running total, of all positions from the first term all the way up to the nth term. Don't mistake a single building block for the entire wall. Second, be careful not to use the coefficient of n as your first term. For instance, looking back at our first example where a sub n equals 3 plus 2n, some students see that 3 and immediately assume that it equals 3. This is incorrect. As we learned in our step-by-step procedure, the first term, is the value of the term specifically when n equals 1. To avoid this error, always make it a habit to substitute n equals 1 into your expression to find the true value of a. Finally, watch out for calculation errors when finding the common difference. When you are calculating d, you must subtract in the correct order, which is a sub 2 minus a sub 1. If you accidentally subtract the other way around, a sub 1 minus a sub 2, you will end up with the wrong sign, meaning your common difference will be the opposite of what it should be, which will throw off your entire sum. Now, before we wrap up and look at our final summary, I want to pause and discuss some common pitfalls. Even if you understand the steps we've just practiced in our examples, it is very easy to fall into these 3 traps, so please pay close attention. Keep these 3 points in mind, and you will be well on your way to mastering these types of problems. Now, let's move to our final slide to review the key takeaways. Key takeaways. First, remember that an nth term expression, which we denote as a sub n, is essentially a rule or a formula that allows you to find the value of any specific term in an arithmetic progression just by knowing its position. Second, it is crucial to remember that you cannot jump straight to the sum using that expression. To find the total sum, your very first step must be to find the actual numerical values of the first term, which is a sub 1, and the second term, which is a sub 2. Third, always keep in mind that the first term, represented by the letter a, is always equal to the value you get when you substitute 1 for n, which is a sub 1. Fourth, the common difference, which we call d, is always calculated by subtracting the first term from the second term, or a sub 2 minus a sub 1. Finally, once you have successfully identified your values for a and d, you are ready to find the total sum. You will do this by substituting those values into the general sum formula. S sub n equals n divided by 2, multiplied by the quantity 2, plus the quantity n minus 1, all multiplied by d. To wrap up our lesson today, let's review the key takeaways to ensure you have a solid grasp of this concept. If you follow these steps systematically, you will be able to solve any problem involving the sum of an nth term expression with confidence. Great job today!